Okay, great. Well, I'm sorry about the slight technological delay, but I'm delighted to welcome Professor Adam Sobey from Southampton University, where he's the chair of the Data-Centric Engineering in the Maritime Engineering Group at Southampton. And he's had a long history, I think. I hope that's not, if I can say that, a long history of applying data-centric engineering methods to maritime structures in particular. He's also the program director of the Data-Centric Engineering program at the Alan Turing Institute. So if there's anybody more qualified to talk about data-centric engineering, thank you.
Thank you very much, everyone, for coming to attend. It's very strange that at 37 I got my professorship and was talked about as a young academic, and now I have a 39 and a long history. So it appears to be the tipping point. It's just as you're hitting on 40. Anyway, it's good. I'm going to do a bit of an introduction to the Turing Institute for those of you who haven't seen the new strategy, a little bit about data-centric engineering, and then I'm going to try and talk through 3 continuous learning, reinforcement learning projects that we've been involved in. One that kind of, I think, motivates the reason for our research, and then sort of 2 solutions to that problem. Hopefully it's all interesting. If I run out of time, then I've left the least interesting one to the last. So hopefully we get through the nice stuff first. So for those of you who don't know, the Alan Turing Institute is the UK's National Data Science and AI Institute, formed in 2015. It's headquartered at the British Library, so the picture at the top is the office space, if that entices you to come and visit us. And if you go left past those sofas, then you come out in this nice area where all the books are. And hopefully we'll see more of you coming through the doors to kind of come and collaborate and work with us. We added artificial intelligence to the remit in 2017, which is when Exeter joined, and Southampton. So obviously 2 of the strongest AI universities in the UK joining at the same time. It's nice. And we all paid in £1 million a year to be part of that institute. So that was quite a big commitment from the universities. But I think also EPSRC government felt it's a bit of a Russell Group club. There wasn't really access to perhaps a wide body of AI specialists. And so we've been put under pressure. And I think also ourselves are very keen to do this as well. So while it's been a push, it's also kind of a pull from people involved to expand the number of university network partners, which increased in 2022 to some number that I can't remember, and 2023 to 65. So this is our list now of current partners that are engaged with the Turing Institute. It's about half of the 140 universities in the UK. So we're getting a really good commitment. Some very strong universities like York just joining us. Some really nice engagement from places like Strathclyde and Plymouth who just joined, who are really engaging across programs. So hopefully it's a nice way to meet people from a wide range of different institutions and different disciplines, all focused around data science, AI and machine learning. And my personal view is that really improved my skill set since I first engaged with the Turing 2019. So 4 or 5 years of working amongst some of the best people in the UK in this area, I think just really helps you have those coffee conversations that make you read papers that you wouldn't normally read. With so many people involved in so many universities, we have about 1,000 people engaged with the Turing over the first 5 years or so of the Institute. And I think it's felt that with the expansions of more universities, that could have exploded somewhat. And working with academics is like herding cats. So everyone's off in their own area, doing their own thing. And perhaps that makes it very difficult for industry to actually engage with the Turing and to see what's going on. So it's been decided to perhaps reduce the breadth of activities down to grand challenges. And each of these will have a director who's now been hired, but who's not been announced yet, but over the next few weeks it'll be announced, all starting activity around these sort of grand challenge areas. Probably not that surprising to anyone who keeps up with UK government, as these are UK government areas. Obviously, we know where the funding's coming, so it's important to engage with that. But environment and sustainability, defence and security, health, and then foundational data science and artificial intelligence, which is around the core for fundamental research areas compared to the impact. And I think, like speaking to people at Exeter, this is probably some really good opportunities for you here. Environment seems very strong here. You've got the environment CBT, lots of work in those areas. I know Exeter has one of the biggest defence and security portfolios of any university in the UK. So again, potential to engage in those areas. I think defence and security has been quite cybersecurity based. So perhaps adding more of the defence side could be some interesting work there. So I definitely think there are big opportunities to engage with the Turing on those grand challenges, and keep an eye out for the new directors to work out how best to engage. Underneath those grand challenges, we also have programs. So these are kind of cross-cutting themes. So for example, data-centric engineering, or ISIT, does some work in environment. We do some work in defence and security. We do a little bit of work in health, and we also like to think we do research into AI that's good. So, we go across all of those, and these are sort of the programs that then do that, across delivering some of that work. It's not been totally decided whether public policy will be a grand challenge or a program, so there's still some fine details to work out amongst some of these things, but I put them on a slide, and whoever's watching this recording in like a year's time, I'm sorry if I got it wrong. But we have a finance and economics group, looking at how we can kind of look at digital economy and the impact that AI will have across those sectors. Digital twins, which works across infrastructure, health, and environment. So things like a digital twin of the Antarctic and how that relates to digital twinning of the heart, and how we can share some of this understanding across these different places. Data-centric engineering, I'll talk a bit more about in a minute. Urban analytics, which is around smart cities, spatial temporal modeling, people's interactions across large spaces. For example, great work on cycle routes in London, and how we can improve cycle routes in those areas. Tools, practices, and systems, which is around open sourcing, and a group around innovation and impact, how we sort of take the work that we've done and put it into industry. They've developed this thing called the Turing Way, which is a sort of growing best practice on how we kind of open source material. Really useful for anyone sort of setting up GitHub repositories and those sorts of things, and support for academics who've done something amazing but can't bother to turn it into something real. There's kind of mechanisms within the Turing to support that process. And I think that describes a relatively large amount of academics, who aren't interested in that commercialization, but where the Turing is kind of nicely situated to sort of support that going forwards. And then a public policy element, which I think is super vital to what we're doing, because at the end of the day, if the public don't like AI, we won't get funded for AI because the government will struggle to fund it. We will get restrictions on how we work. The ethics forms will get longer. The chance to get funding will be more difficult. So I think it's really important that all of us as a community are engaging with the public and trying to be sensible around the conversations around killer robots versus chatbots and these sorts of things and where we sit. So I think a really good opportunity to engage and to learn those skills as well, because I think for many of us in computer science, engineering, the more applied side, we're perhaps not great at engaging with the public or in policy as well. So there's sort of support for that. Within data-centric engineering, our vision is to lead the development of new approaches of data-centric engineering. So that's the sort of impact side of things. We want to basically make sure that we're putting tools out into the real world in terms of reducing emissions and improving safety. So there's our kind of core challenges. We'll do that through the delivery of new tools and practices. So some research elements, training, where we really want to engage at all levels, from apprenticeship through to CPD, to sort of like high-level C-suite type training to support these new business models, and also policy changes as well. How do we change regulation and standards to allow us to use these tools? We have 4 priority themes, which we agreed with Lloyd's Register Foundation, and we're looking to expand these with additional funding as we go forward. So this is our kind of core starting point, where we're working in marine and maritime, which is the group that I used to lead before I took over the program. Digital manufacturing, which is, marine and maritime is run by Kimberly Town at Plymouth University, who's a cybersecurity expert. Digital manufacturing, which is run by Alexandra Brintrap from Cambridge, who leads their supply chain group in the Institute for Manufacturing. Critical infrastructure, which is Graham West, who's part of the Advanced Nuclear Research Centre and has done a lot of work on predictive maintenance of very large structures in inaccessible places. And we also have a humanities, arts, and social sciences in data-centric engineering theme lead, which is Drew Hennant from Edinburgh, who's a creative arts researcher, professor up in Edinburgh, with the idea that if we want to meet these grand challenges, we can't do this in a purely technical aspect. We have to understand the societal impact. We have to understand how this relates to public policy. We have to be able to communicate. And so we really need to bring a broader range of skills together to be able to do something. And this is sort of the aim of that program. How do we utilize these different disciplines that we perhaps haven't engaged with as much from a STEM perspective? And by actually taking these people and embedding them into the program and working alongside our postdocs in engineering, we're really hoping to see some change in the way that we think around problems. For example, where does your lithium come from? Probably comes from either China or Africa. And so, we've got problems around some geopolitical fallout, but also do we really want to be going and thinking of Africa and paying a minimum price for our lithium and to decarbonize ourselves? And I think there's some interesting conversations around how society equitable our decarbonisation actually is that we're kind of ignoring because we're so focused on net zero. But I think it's worth having those conversations and understanding how we can actually balance these different perspectives. That's, I guess, what we're trying to do on that theme. No problems. So, some examples of some projects that we're working on to give you a flavour of what we do. We're working with the Centre for Emerging Technology and Security in the Defence and Security Programme around a white paper on the status of cybersecurity and renewable energies. There were about 100 wind turbines knocked out of action in Germany through a cybersecurity attack a few years ago. There's been other cybersecurity attacks on wind turbines. UK is installing 1,000 wind turbines off the coast to protect our energy, and therefore we probably want those to be safe and not be able to be knocked out. So we need to start looking at how we defend those against attacks, and where AI can play a role both in attack and defense. So it's the sort of policy piece that we're starting with the aim to write a proposal based on that to actually start doing some of the technical work. Was part of it.
What's the purpose of doing cyber attacks on wind turbines?
So if you knock out the wind turbine, then there's no electricity. So it's like terrorism.
Like economic war. Or...
Yeah, so terrorism, any of these sorts of factors.
So do we know like who is committing those attacks?
I don't know. Maybe someone knows that. I'm not aware of this part of what we're trying. So quite a lot of the industry is ignoring this as a problem. As much cybersecurity, so I guess we're trying. It's one of the reasons why we want to do some of this work is to sort of raise the profile of it and to get people to start thinking about it within the industry and what they can actually do. It happens in shipping all the time, but it's actually ignored. Insurance don't like to pay out on cybersecurity, so they generally put it down as an accident. But when you have a boat that suddenly gets into a 5G zone and suddenly goes on course, crashes into the rocks, reverses, and then drives back into the rocks, it seems like a very strange accident to me. So, yeah, interesting how some of these elements are sort of being a little bit hidden at the moment. That's sort of like some of what we're trying to understand and see how we can have a solution. We've got a AI for Decarbonisation Innovations Virtual Centre of Excellence, and I think I actually got it right that time. Short name advice. I didn't come up with the acronym. It's the Department of Energy Security and Net Zero's centre to look at stakeholder engagement around how AI can support decarbonisation, how they can sort of spend their money. So our first stages have been around sort of that collaborative element. Who are the key people in these different areas who can help us and bring them together? With, I think, just about to secure quite a bit more funding now to actually start doing some real work in this area to sort of support these industries. That's across agriculture, manufacturing, energy, and cities. And so I think quite a lot of different work in that area. And then on top of our sort of policy work, we've got this digital twin, the short straits. 60% of trade comes out of Dover across the Calais from the UK. But anyone here probably seen those long queues that can occur at Easter and things. So we're trying to work out how you can predict those queue times and what you can do to instigate reduction of the queue times themselves. So a very large digital twin, it's got the road networks down to Dover, and you've got the waterways across from Nova as well, potentially rail networks as well at some point. So thinking a little bit around how we can kind of develop these digital twins. And I think it's kind of an interesting project from a practical standpoint of how we actually do that with the data that we've got available to us. In terms of research, then I think fundamentals-wise, we've traditionally been very good at things like uncertainty quantification, fundamentals of digital twins, sampling, Bayesian methods, physics-based machine learning. So there's sorts of work going on in the stats department, engineering department, across the university. I think moving forwards, and this basically came from my interview when I applied for the job, was around sort of like the future, but I think we're probably already there in terms of engineering. You know, we're starting to see reinforcement learning being applied in applications for control. Transfer learning is becoming more important for scale up multi-agent systems in various areas for example, EV battery controls and that sort of thing. AutoML and large language models are all kind of like things that we do. So I see like a big move for engineering, not just around the sorts of things we've traditionally done, but also now starting to encompass AI. And how we actually absorb that knowledge into engineering is going to be very challenging for us, and keeping up with that knowledge base is really difficult. But I think it's very exciting at the same time. The potential is huge. And just as a kind of point of interest, we just opened our Spunk Center of Fundamental Data Centric Engineering. So Spunk are a company in the US. They gave us a nice big gift to spend on whatever we wanted. So I thought some fundamental research to support the program was good. I think the development of data models is becoming increasingly simple. I do it in companies all the time. We're developing models for up to 60 ships at a time, and that's not too bad. The problem is the scale up. One of the companies I work with has 16 data engineers for their 60 models, and they want to go to 10,000 ships. So that's quite a lot more data engineers you're going to need. A large car manufacturer we're working with wants to have a digital twin of every component on every car when they go autonomous in about 10 years' time. That's quite a lot of models. They have 60 million cars on the road right now. It's assuming 10 components. It's like 600 million data models. How are you going to build that? And you could hire every data engineer globally, and you still couldn't make that many data models. So if we want these techniques to become pervasive, we have to find ways to automate the process. We have to be able to take the data from the sensors, clean it up, put it in a database, pull it through, create a model, quality assure it, work out the update times, and communicate it to the end user, all in a way that isn't impacting huge amounts of human time if we want it to scale. And that communication should probably be bespoke. Check engine lights, half of the people just ignore it and will drive around with it on for many, many years. Other people will pull over to the roadside in a panic that their engine's going to explode. Neither of these is the response that we want from a check engine light. Can we use things like Facebook profiles, Instagram profiles, to understand how to communicate to people better, so that when our digital twin or our models interact with people, that it's more bespoke, and then it gives the information that they want. Again, we probably want our model that's talking to a person to talk differently to a ship's captain and use different language. So how do we build dictionaries that speak to different professionals compared to end users? So these are sorts of technical problems we're looking at solving. We have 3 postdocs working in the team, very interested in people working in similar areas to see how we can push this forward. Because I think what we're trying to do is a bit moonshotty, and it's definitely a bit ambitious for a 3-year project with 3-year postdocs. So the bigger community we can help build around this, the more chance we have of some success, perhaps. So that's the kind of background stuff. I don't know how long to go with that one. Quite a long time. So we'll talk about my research projects stuff now. All around learning in continuous environments, which I think is a really interesting area and one of the more challenging parts of reinforcement learning. So the idea being is that in many applications, we want to do, we can sort of do some reinforcement learning and then apply it into the scenario. That's very safe because we can validate the models and we can understand the behaviors. But in many of these areas, the background will be changing somewhat. So the way in which the environment might change slowly over time, and that might invalidate our model. It means that we have to keep constant checks, or we have to come back and retrain the model as everything's changing. And for example, in supply chains, that can be quite rapid. The fact that you could have a very different sort of demand across different time periods. Something like COVID affects it, Christmas affects it. Some of these are predictable, but how do we build models that can actually deal with these scenarios? So we probably need learners that can continue to learn over long time periods. And what we see in the supply chain literature is there's a lot of multi-agent modeling, but none of it looks at how the environment might change. It has a very static environment, does some pre-policy training and perhaps changes the environment afterwards, but doesn't look at how the agent adapts. And what I'm particularly interested in is how similar do the tasks look to an agent. So if I look at a manufacturing task, I have an idea of how similar it might be to solve. Does the agent look at that in the same way as I do? And the different agents look at it in the same way to each other. So if I use different architectures, do they actually seem to think that the same tasks are similar to each other? So we built a simplified, well, we didn't build, Cambridge built a simplified supply chain environment that we stole because it's quicker to do these things on someone else's work. And it's basically got three different agents. It's got a factory agent, a warehouse agent, and a retailer. We have some customer at the end who says what it wants to buy on each day, and effectively then the sort of like it checks with the retailer to see if there's any stock within there. The retailer makes orders to the warehouse, and it takes a day in between for it to get to that time period, and the warehouse can ask for stock from the factory on each of the different turns. So they're all acting independently. They can all decide how much they want to ask for each time, and there's a sort of like time period it takes to go through each of these different points. The actions for each day are the amount of stock that they can order. So factory and warehouse can order up to 30 items, retailer can order up to 10. And there's also a reorder point of 0 to 4 days, which basically puts a stop on whatever's happening, and they basically look to see whether they want to reorder. So effectively, it makes it a little bit easier for the supply chain to look after kind of the manufacturing processes. It doesn't have to make a decision every single turn. It can just say, I don't want to make a decision for a few turns. The reward-based system is that for each factory and retailer inventory in stock, there's a charge of 1,000. In the warehouse, it's 5. And there's a stock out cost of 1,000 as well. So if our customer asks for something and there's no stock at the retailer, it costs us 1,000. Also, if we get stock out 3 times in an episode, it finishes. So effectively, we kind of finish early and we say, okay, that was a bit of a failure. Let's move on to the next time. The maximum amount of inventory in each of the different places is 30. So effectively, we can only go up to 30. And if the retailer asks for a certain number of items, for example, from the warehouse, and it goes over 30, it's clipped to the maximum amount it's allowed to have in the inventory. So there's no kind of penalties for that. So large requests basically can just be clipped to the maximum inventory. What's traditionally used in this is a stochastic demand. So each time we roll the dice effectively, and we see what happens. So we end up with sequences of random numbers going forwards. We really can't tell what's happening. And I think that's quite likely in some quite agile manufacturing processes, but perhaps that's quite an extreme example. On the other hand, when we get our variance down to 0, then it's the same value all the time, so an infinite string of the same value. So it's quite a big jump between a very, very stochastic process where it's changing every day to an infinite string of the same demand. And so we added this kind of batching demand into the process, which has the same distribution as the stochastic one, but it just groups all of the demands so that you get runs of those, and that gives you a somewhere in between the two processes. So now we have a bit more fine control over the tasks, and we don't just have these big, big jumps in tasks. And I think that's important for our continuous learning purposes. We tried 2 different learners. So PPO, which I think is pretty much stock, is probably one of the best reinforcement learners on these things if you're not looking at distributed learning. And recurrent PPO, which has like a time series understanding associated with it. So we just add a layer of LSTM that works into the process, but now it has some memory. This is becoming very popular in the supply chain literature, so a movement from PPO to RPPO, and you're sort of seeing that. I find that quite interesting, the fact that they haven't really got very many sort of lean manufacturing processes. It doesn't make sense to me if it's stochastic to have a recurrent element, but I can only review the literature. and sort of talk through. So we tried it on each of the different environments, each in turn, to see what happens. And effectively, it's not very exciting. For the batch environments, we get very similar reward graphs to each other, whether it's batched in 10s or 7s or 3s. For PPO, it's giving a very similar reward learning curve, and there's not much change there.
So I can ask a question on the previous one. Sorry, sorry for that. Can you say, if I understood the recurrent one, just to understand, what is it recurrent? What is it using? Is it a prior date? Is it trying to figure out sort of the batch?
It's got the memory, previous days demand.
So just to check also, conceptually you said before, if you had stochastic, you wouldn't think this doesn't make any difference, right? But equally, you should very much expect this to the batching to be the driving factor. If the recurrent makes any difference, it's because of the batching.
Exactly. Yeah. Okay. That's the kind of idea anyway. That's why we thought we'd sort of put that in. We'll see the results then, whether I can guess what AI is doing. Turns out I don't. So effectively in the PPO, the sort of the behavior across the different batches doesn't really look any different to me. I can't really see any sort of interesting behavior there. If anyone has, we haven't quite submitted the paper, so let me know. Rewrite some stuff. Stochastic environment, again, very similar type behaviors. There's an ever so slight difference. We did 5 runs on these, so that there's not a huge amount of variation in the behavior, and we're not really seeing very much difference. The RPPO batch environment ones look a little bit more ugly to me. I was kind of expecting some quite nice results on this, but we're actually getting ever so slightly lower rewards, perhaps than the PPO. I mean, the numbers are in the paper; they're very similar to each other, and some slightly odd behaviors where on the batch 10 we get like some decrease in performance after some period of time after a peak, but nothing kind of outstanding. And again, like the same thing on the stochastic environments. There's kind of like a little bit of lower performance, I think, on this, if I remember correctly. But it's all very similar stock kind of behaviors to each other. The only reason I present these quite boring results is that I think they help to explain what's happening in the more interesting results in a minute.
Sorry, are you showing single learning runs there?
No, they've got the district. There are boundaries on here, but I think they're just very, very faint on here.
So how many runs are there?
Yeah, there isn't that much variation in the behavior really. It's quite repeatable, right? We could have done more simulations, but I feel at this point just the repeatability is pretty good, so I'm pretty happy. I'm sure the reviewers will send it back and ask for some more. That's always the case. I think the person doing the work was just bored, so we're going to try and submit and see what happens. But what's interesting is that there's actually 2 quite distinct behaviors actually happening. So if you look at the left-hand graph, you can see that the line is basically the amount of stock in the factory. It's just flat at 0. There's literally no movement. It never moves anything ever at any point. On the right-hand side, you can see the RPPO on the batch environment actually always some stock. So there's little bumps and wiggles here. So there is something going on. And what it's found is like this cheat basically within the environment that no one else seems to have found, which is that if it stocks out early, it's actually because the stock out reward is so low, it's actually better to stock out early, reduce the length of the episode rather than taking the hit on inventory costs over a longer time period. So it's basically just saying if I end the game early, I can basically not have to spend very much reward, and it's very smart. It's good. And actually, like PPO does that a lot. Our PPO, because it's got like some semblance of a time history on the batch environments, it actually tries to play the game a bit. And so it does actually kind of like start to order some factory stuff. The interesting thing is that the reward benefits are not really there. It's not actually really gaining much by doing this. So the environment setup is just quite bad for what we're trying to demonstrate from a supply chain purposes, or is unrealistic. Luckily for us, because what we're interested in is this continuous learning, just having different strategies probably allows us to sort of understand a little bit about what's going on. But I thought it was quite interesting that it's managed to find that, and that basically this playing the game correctly was like the worst decision in this scenario. And I think especially from an engineering perspective, people need to understand how important it is to set up those rewards. But also it must mean that like literally no one's ever looked at the actions before in that space. They just plotted rewards and be very happy and comfortable with the end result. So it's some interesting kind of learnings more on that side than perhaps the bits. But then when we look at the continuous learning environment, effectively on the batch problem, and this is running the batches each way just to make sure that there wasn't an advantage to running it one way and then another way. You can see that basically there's a learning period and it can transfer its learning very easily. It has the same strategy every time. It's going to cheat. It's going to basically try to reduce the length of the episode as quickly as possible, and it can apply that across everything and get a very similar model. In the same way, the stochastic one kind of gives you a little bit of variation on this, but there's basically a very similar element. What's interesting is when we do the RPPO with the batch, because it's actually trying to solve the problem correctly, it actually can't transfer learn very well across these environments. So despite the batches being in 3s, 7s, and 10s, it's quite a similar task, really, in my view. And it's more similar than, say, CARPOL, which is an example that's commonly not used in computer science now because it's too simple. This is even more similar, but it's kind of struggling a little bit to deal with that. I think it might be just where maybe it tries to move between cheating and not cheating or something similar to that. But we're getting a very erratic behavior in the RPPO in comparison. And in the stochastic environment, we get slightly less erratic behavior because it's starting to cheat again, because it can't solve this. The LSTM network is giving it no advantages. It can go back to cheat mode, and while it's slow to learn, it does get to a place where it can do that. So that's quite interesting as an example of some of the things that we're struggling with in continuous learning, basically around transfer learning and around catastrophic forgetting. In that the RPPO shows a greater instability on all the problems, and it seems to be like leading to an over-optimization of its strategy that it then struggles to transfer across these different tasks. Whereas the PPO learner has similar strategies, and so therefore it can transfer learn really easily. It has like the same way of treating every task, and it can work across each of those. In all of this is quite a lot of gaming the system, so it's definitely an imperfect environment. I wish I'd known this when we started off because we could have done something a little bit different, although I think we know how to fix it now. And we've shown that basically I think continuous learning is possible on these problems if it creates similar strategies. But we need to understand a priori how similar those strategies are going to be, and that can be very difficult before we do it. So how do we go around understanding whether we can continuously learn or not before we put something into practice? So some of the problems that we were sort of talking around here are then stuff that we tried to solve a few years back. So it's a sort of reverse time period thing. And we haven't applied these problems to that supply network issue, but I just thought it was an interesting kind of summary of what we're trying to look for and trying to stop. We looked at this thing called active adaptive perception. And this is really with a goal of looking at things that have very sparse rewards. So how do we solve problems in these spaces? It's really difficult for reinforcement learning to do. So we have limited knowledge a priori, very sparse feedback systems. The designer can make few or no assumptions about the environment. And in our case, we're using this partial observability. So it's maze searches, but it's just really important to remember that the AI can really not see very much. It can literally just see what's in front of it. And so actually many of the spots on this look very, very similar to each other. And I think that's like the kind of bit that people don't get, because when you look at the maze, it's quite easy to solve in theory, but similar things. Again, we drop it randomly across the maze, so it doesn't know where it is when it starts, so it's got to find out where it is. And it doesn't know where the terminal state is initially, although we keep that in the same place, so over a number of generations, it starts to find the same spot. So it's like dropping you somewhere in Exeter. You'd be able to work out where you wanted to go and walk straight there, but if I dropped you in Aberdeen, you'd have to take some time to work out a strategy to get yourself back down to Exeter, and it would be a much more challenging task. What we did was we basically created like a sort of neurosymbolic type of approach with this, where we've got this instruction set, which basically has a north, south, east, and west representation, and then it also has this ability to both call and adapt this perception module, which is like the bit that we're interested in, which is we ran two different versions of this, a neat neural network and a DRQM with modifiable instruction sets on top of it. So effectively it can sort of create instruction sets of north, south, east, and west, or it can say call my neural network and see what I want to do.
Can you say a bit more about what you said earlier? Very little knows known about the environment. Like, what is it that it doesn't know? So it knows, first of all, it knows that it can turn in whatever directions, but what does it not know that you would normally assume that the reinforcement learner would know? So what is it that you're withholding in this particular example?
Yeah, so in this case, it doesn't know the space, it doesn't know what the goal is, it doesn't know how many goals there are. It's basically just dropped, and it just
and it knows what itself can do, like turn.
Yeah, exactly. It knows what it can do, and we're basically trying to explore the space to see what happens. So nominally, it should be really easy to solve. So this is an example of one of the more complex mazes that we checked out, and the reason we stopped here is we did try some even more complicated ones, but AI was just falling over. So this is like the limits of our kind of capabilities with this. So we put in just a raw DRQN learner, which isn't using our active adaptive perception element. And this is a heat map where red shows where it's spending most of its time, and blue is showing where it's not spending any time at all. And it's randomly sort of dropped in there. The arrows on there basically show what the most popular command was on each of these different spots. And the problem is, because it doesn't see goals very often, it's randomly dropped in and it has no policy. It never even finds the goal. And so it never has any chance of learning. It just moves around at random in these little pockets. And because they're really tight to get out of, it really struggles to do that. The chances of rolling enough lefts to move yourself out of the bottom zone in a row is just too small, and it ends up getting stuck in these wedges. And so we end up with no decent performance, which is kind of like really interesting that it's just that bad. When we add this kind of active adaptive perception element to what we're doing, this ability to create this instruction set, what it does is it has two elements. It creates a strategy for getting out. Its initial search strategy, which is the instruction set. And so these instructions it kind of uses to kind of create a way of getting out. And then it has like a memory that it uses that it basically calls the neural network part. And that's where you kind of see the little dots. Whenever it gets to those points, it knows what it's doing. It goes, I recognize this point, call the neural network, and memorize my way to the goal. And so you're actually kind of able to get quite an effective way of getting out of these spots. I think it's really interesting, shows how difficult these sorts of like sparse reward problems are in a continuous learning environment. I think also it shows that perhaps just having very large networks and lots of data isn't enough if they have sparse rewards. We need to create kind of tight training processes or pre-train things to get out of there. This is a relatively simple problem to solve. So I think like this sort of approach is kind of interesting from a sort of neurosymbolic approach, a balance between the two, where we investigated this with the ability to modify and utilize this perceptual module in completely self-chosen ways. So it's learning to learn basically what should go into that neural network, and it's learning to learn how, when to use that network as well. And so it's able to do that. Allows it to invent these strategies, and it does this by learning to modify its own learning operational behavior. And the sort of raw learner itself is completely capable of doing that in good time periods. So I think moving forwards, we need to probably think a little bit about how we develop learners that aren't just based on pure neural networks. And I think this is also related then to what we're trying to look at is effective use of data in these scenarios, and we've looked at this thing called task capacity, which effectively in a continuous learning environment, let's imagine we have a number of tasks. So we have tasks 1, 2, and 3. And we're going to assume that task 1 is one type of task and it's red, and tasks 2 and 3 are more similar to each other, so they're in green. And effectively we have like a series of points that we're basically going to work through. And we've got our policy at the bottom. And effectively, it's going to see this observation, it's going to create an action. So on the first step, effectively, we kind of create some learning around the red task, but then we move to our second task, which is a green task, and we effectively kind of unlearn a little bit of what we learn. We then move forwards with some green tasks, and we can keep kind of like pushing forwards what we want to know until we get back to a red task again. But at this point, our policy is like kind of like only understanding how to do green tasks, and it will perform very badly on this REST task. It's catastrophically forgotten what's happened. And so we know this happens a lot in all types of AI and machine learning. So how do we solve that? Well, it's really easy. We have three policies, right? We have 3 tasks, 3 policies, and basically we can work through the different scenarios. So on the first task, we have a policy associated with our first task, a policy associated with the third one, a policy associated with the second one, and we never unlearn any of the behaviors that we wanted to learn. So we now basically have a situation where we can ensure we don't have catastrophic forgetting. Obviously, the problem with this is that if I have a million tasks or a billion tasks, I now need a million or a billion different policy learners. I need to have some way of working out which task is which, and how do I subdivide tasks? Do we have a clear definition of what a task is in AI? And I'm not sure that's actually the case. We have some understanding that they look similar to each other, but is in that action space, or is that in reward space, or is that in state space? I think tasks kind of look similar in each of these spaces. If I swing at a tennis ball and I hit it, then or I miss it, they look very similar in action space, but they look totally different in reward space in terms of points that I get. And so I think our definitions of tasks are tricky. So splitting this up is difficult. So I think we're sort of thinking a little bit around, how do we sort of look at this in a more formal methods way, formal approach. So we sort of tried to look at this task capacity. The idea that for any set of tasks that are in a place, a policy will have a maximum amount of tasks that it can learn. So can we predetermine the number of representations that we require for lifelong learning? How many different ones we would want to see? We want to reuse the same policies for the same tasks or similar tasks to each other. So we use the minimum amount of data and the minimum amount of RAM. And we want this to be model agnostic, so we don't want it to be a set approach. We want it to work across all approaches. So really what we're saying now is if we go back to our initial example, there's probably a set of policies, in this case maybe 2, that actually is optimal in terms of like the learning data and in terms of the RAM that we would want to use, but with the red task being learned on one policy, but all the green tasks being learned on the same policy. And now using exactly the same representation, we have a much clearer understanding of the sort of green policy and the red policy. And it's not just a diagram, we actually ran this, it does actually work. So we tried it on 2 different approaches. We wanted to see whether this works on DQN networks and PPO networks as 2 of the leading brands of kind of ways of doing this. We tried it on an 18-task Popman mazes, so the bottom picture. And we tried it on Carpol as well, which has some nice things in that the tasks are very similar to each other. So you can't get much more similar than Carpol type experiments. So there's kind of the Popman, which is quite different to each other. In some cases, some things give negative rewards. In some cases, they give positive rewards. So there's an awful lot of interference in this. The same observation can give you very different rewards each time. And so it's very difficult to understand what you should be doing in those scenarios compared to Carpol, which is just balancing out the pole. It just gets longer or shorter. We developed some testing metrics. I haven't really talked about them. They're in the paper if you're interested, but around things like forgetting ratios, transfer ratios, policy spread, which I think is interesting to see how different policies might be to each other. And I think it's like that we don't look at very often. And again, this idea of task capacity, how many tasks is an individual policy able to learn? We've developed an adaptive version. It's not very good, so it's something I'd like to work on a little bit more. But the idea that effectively, in much of this, the results I'm going to show most, the unadaptive version is we just put a certain number of policies in and just let it kind of predetermine which tasks it would learn. There's an adaptive version which gives similar-ish results, but I would like to see some improvements on that as what we did. So on Carpol, this is a series of learning curves. Each of the different colours tells you a little bit around the sort of number of policies that we used. And on the left-hand side is the DRQN network, and on the right-hand side is the PPO network. So I think the first thing you can see, obviously, is very, very big differences between the 2. There are 2 types of policy. We see the PPO is really not made for like a multi-policy approach. It's very well defined for a single policy, and actually we don't get much improvement this way. But with the DRQM network or DQM networks, so DRQM, we get like some. We do get quite a lot of difference in how the policies behave. When we used one or two policies, we actually get very poor performance relatively. Just kind of like a big spike initially, but then it drops down. And this kind of corresponds to what we would expect based on a lot of the papers that you see in reinforcement learning that PPO would outperform DQM. Probably why PPO is kind of more popular on a lot of the tasks. It's generally seen to be outperforming things like Rainbow. Are generally outperformed by different levels of PPO. Not always, but a lot of the time. It's quite interesting though is that when you jump up to a 4-policy network, then we, out of 27 potential potential tasks, we actually get very good performance now. So rather than even a small number of increase in policies, we get a really big increase in performance. And then right at the top, we kind of end up with this 9, 14, and 27 multi-policy elements that all kind of look similar to each other. There's very, very small differences in terms of performance, obviously reduced around for using the smaller amounts. And so it's kind of, you get a kind of quite a slow learning process as well with the 27 policy learner, because it's not seeing very much very often. It has one task, and in a sequence of tasks, it's not getting very much data. On PopMan, we get like a cleaner performance, so this is a more challenging task. But again, we get a very similar type of process. What's nice for explaining this one is it's more gradiated, so no policies at the bottom, more policies at the top. You can see that the 18 policy learner in this case is much higher performance. So you can't match the performance of the individual policy learners in this case. But you can get somewhere quite close with quite a reduced amount of round, quite a reduced number of learning or seeing more or different amounts of learning instances. The PPO learners again don't have very much spread, and so again you can kind of see the way in which that PPO is really built to be a single policy learner and kind of definitely performs better than DQM even with a small number of policies. So we've got this way of basically matching all these different policies and thinking a little bit about the task. So I think moving forwards, it's quite interesting that most people are really just considering single policy instances. They always think about their learner being a single element that sees everything and just grow it larger and larger. But perhaps there are some performance benefits to thinking around this with different elements. With the cart pole instance, then we also tried this on transfer learning, and we managed to apply the 4-policy cart pole learner. From the 27, we were able to extend it to being able to perform well on 125 tasks. So it's a really big amount of transfer learning. I realized that those tasks were all quite similar because they're cart pole, but still it's quite a big spread of things that it's able to optimally do, even with just four policies on that network. There was also a really big difference in behavior between PPO and DQM. And I think it's interesting to think a little bit around how our agents are performing differently depending on the architecture. So I think when we think about continuous learning, we're not really thinking around how those how the agents might see the tasks differently. So we might actually need different task definitions depending on the architecture of our agent. We can't perhaps have just a single definition of what a task is, but perhaps we need to think around that being slightly different. That's similar to human. If any of you tried to do a task and then we did a second task, I might think that task was harder or less hard than you with different life experiences. So, we're all going to have a slightly different view of this. But within our learners, I don't think many people are really considering that the task might change based on the architecture, or the task definition might change based on the architecture. And then we've also derived a bunch of metrics to explore lifelong learning, which I hope gives a nice setting for understanding this sort of task capacity. And how many tasks we might want to associate with them. So it's quite quick through quite a few different techniques, but hopefully gives you some flavour of what we're doing at Southampton and encourages you to come and talk to me a little bit more later today or at another time. So thank you very much for listening and happy to take any questions.